Hello, everyone. My name is Sebastian, and welcome to our webinar, Understanding Connected Data Through Visualization. Today, I would like to show you the benefits of using custom visualization solutions and how they will help you and your users with understanding and gaining insights into graphs, diagrams, networks, and all other kinds of connected data. This is our agenda for today. We'll start by taking a quick look at what types of options you have once you decided to visualize your connected data. Probably most of you have seen various simple or off-the-shelf visualization tools already. So we'll be looking at how we can do better if we spend just a little more time to come up with solutions that are really meant to work with that specific use case we're dealing with. In particular, we see how sophisticated automatic layout can dramatically improve the ability of the user to actually understand the data sets. And we'll take a look at cases where transforming the graph for display only helps in getting much clearer visualizations. I'll show you a number of examples of tailored diagram visualizations that help in quickly seeing the most important data. And then we'll take a look at how we can improve the user experience and working with the connected data in diagrams in general. And finally, I'll show the advantages of integrating a visualization with other systems and data sources. And after that, I'm happy to answer the questions that you may have. So what different types of tools do we have for visualizing connected data? Of course, there are these absolute low-level viewers that help you look at the raw data. This could be as simple as a text file, an Excel sheet, an interactive database console, or textual table browser that will give you actually all the data in raw format. You will get to see raw values or symbolic names and IDs that need to be looked up or interpreted manually, so this can become very inefficient quickly. But there are also standalone, off-the-shelf generic graph viewers available. They are mostly optimized to be usable even by non-developers who don't understand or who don't need to understand all the technical details of how the data is stored. Many of the simple mappings from data to the visualization can be achieved with these tools, and sometimes they even come with a few graph analysis algorithms that can help in understanding the graph. However, if multiple data sources need to be combined, or if the data is stored in a format that does not match the format that these tools expect them to be in, they can fail miserably. So that's because their ability to map the data to information on the screen is limited to a few predefined templates. If you have a very specific non-generic use case in mind, they won't help because more sophisticated mappings are simply not possible. Thus, today I'd like to focus on software programming libraries for visualization. You can't just simply click and run them to start looking at your data, but instead you need to have or be a software developer who will set up or create an application for you specifically designed for the data you're looking at and the use cases you have. Software libraries enable you to create new applications from scratch that you can use or give others, maybe end users, to inspect or work with your or their data. And you can also integrate these features into your own existing applications and dashboards, both on the desktop, on mobile, and the web. Most of the time, these will be white label solutions that can perfectly fit your own corporate design or your existing applications look and feel. As the creator of the app or widget, you can decide where and how the data is sourced. You can transform it. You can determine its precise visualization, what interactions there are, whether and how the end user can modify and edit the data, and how all of this can be integrated into larger IT infrastructure and optionally with other services. In the next slides, I'll show you how the extra effort for the implementation of a custom visualization app pays off quickly. I'll be using our software library Y-Files for the visualization of graphs, diagrams, and networks. More specifically, here I'll be using Y-Files for HTML, one of the members of a whole family of graph visualization SDKs. It's built for web technology-based applications and thus works well on the desktop, on tablets, and mobile devices alike. YWorks also offers equivalent software libraries for other major programming languages and development platforms. And the unique selling points that we have include, we have the most complete set of sophisticated automatic layout and graph analysis algorithms. We have a flexible and very powerful viewer engine, and most of all, unmatched customizability and extensibility. We're now going to see how Y-files can help in creating a custom visualization application that makes use of advanced diagramming capabilities. The data that we'll be looking at is from this year's graph drawing contest at the International Graph Drawing Symposium that was held just last month in Prague. The task was to explore and visualize data from the Marvel hero character universe and the movies the heroes, the characters appear in. I'll show you some sample code and explain how it works. This is real working code, and for those of you who know modern JavaScript or at least a little programming, it should be easy to understand. But don't be scared, it's not that important. And there'll be plenty to see apart from the code for you. So here we go. We start with importing the data. Using a programming library, really any type of data source works for importing the data into the visualization, as long as you have programmatic access to it, of course. So it could be a simple JSON fetched from a dynamic service or even just a static file, or it could be XML, text, CSV, or some binary format even, really anything. And of course, if you have convenient third-party database connector implementations, they can help a lot with that task too. In this specific example, I loaded a simple data set that was provided to us as a GraphML file, but I could also be using a generic, very declarative approach too, or use the low-level API for building my diagram manually. At the top, we see in the sample code, we see the approach that you need to go if you load the sample from a raw GraphML file. It's just one line of code. In the center, there's some declarative approach where we build the graph from JSON data, or it could be any JavaScript object structure. And at the very low bottom, there's the low-level API for creating items manually in the diagram. In all cases, we can store arbitrary data with the elements, and this is the data that we got from the original data source or that we added later. And this can be any kind of data and mostly contains a reference to the original business entity that the diagram is modeling. Usually there are no coordinates associated with elements in a data source, so we would need to start with a diagram like this that has really no layout. We could go and manually untangle the graph interactively, but using an automatic layout often greatly helps us with that task. The result looks quite pleasing, but the insight we gain from pictures like this is very limited. Just stating that the graph is connected and how many items there are would give us similar information. Pretty, but well, useless. We should at the very least add information about the identities of the elements in the diagram. In this example, all nodes have a name property associated with them, and we can display that in the diagram, of course. With Y-files, the layout can even take these labels into account so that they do not overlap in the visualization. As you see, it's just 2 lines of code, one for adding the labels and one for, well, a complex line of code running the layout. And there's options, plenty of options that you have for configuring the layout. In this case, we're just turning on the option for taking the node labels into account during the layout. We can see that the data contains nodes that represent movies and heroes. And this is actually part of the input data, the type of the node. So we can use a simple shape and color coding to add that information to the diagram. As you can see, there's an API for the simple styling. We'll see more sophisticated styling later. For example, we declare that the heroes should have an octagonal shape, should be filled light blue without an outline. And then we just iterate over the complete graph, filter all the nodes by type, and for each of those hero nodes, we set the style to the hero style. So far, this is still all very, very basic, and all of this previously mentioned tools that you may know of should be able to give you very similar results. but we haven't really gained a lot of information about the graph. We can do a lot better with only some more lines of code. For example, we could run graph analysis algorithms to show important players in the graph and display it directly in the same visualization. Here in this example, we are showing a simple heat map of degree values in the graph, and we also add arrowheads to see directed relationships in the graph. As you can see, there's just one line of code where we retrieve for each item in the graph a value between 0 and 1, which will be used by the heat map component to render these nice heat map visualization. But in this case, in fact, if we put the two types of nodes into separate group nodes and rerun the automatic layout algorithm, we start to see some structure. The graph in this case actually is bipartite, and each node belongs to one type of group. This is a very simple case, but it could be more complicated, and we could have multiple group relationships per element. Bi-files allows you to render this type of group relationship with simple group nodes like this, but it's not particularly useful in this specific case where we just have two groups and where there's really no nesting. Bi-files would allow you to use any type of nesting and to use drill down, and so that you can have interactive collapse and expand operations. But again, in this specific case, they would be quite useless here. You can see in the API, there's a simple single line of code for creating group nodes and tagging those with an additional type so that we can discriminate again between them. Another option that we have at our disposal is this kind of visualization. If nodes belong to multiple groups and those groups could overlap, a visualization like this is better suited. However, again, in this specific case, we can just instruct the layout algorithm to explicitly partition the canvas into cells, in this case into two rows, and have all the heroes in the top row and the movies in the bottom row. We could also even visualize these cells, but here it would not really improve the situation and would just disturb the diagram. In fact, for this kind of graph structure, where there are two sets of nodes and connections only ever go from one set to the other, we can use a more sophisticated layout that makes this clearer. Once we apply the hierarchic layout, every hero and every movie is on the same horizontal axis each. This results in a much wider layout, but immediately it becomes a lot clearer to the viewer that there are no connections in between the movies or in between the heroes, and that every edge only ever goes from heroes to movies in the data. In the code, in this case, we explicitly told the algorithm to put nodes which were tagged with the type hero into layer 0, which is the top layer, and the other ones into the second layer. But given the graph structure that we have, this would have not really been necessary, in fact. From here, we can add more information to the diagram and use it for further constraining the layout and cleaning up the visualization. Each movie plays in a certain year in Marvel Universe time. By augmenting the visualization with that data and telling the algorithm to place the movies in a constrained order, we can add that information to the diagram. This is just one of the constraints that the very flexible hierarchic layout algorithm supports. There are many more available, and we'll see some of them in the later slides. As you can see in the code, there is an option called sequence constraints. And for each item, there's various ways we can configure the sequence constraints. In this case, where we have a comparable value available for each element, which is the year that the movie plays in, we can use that information to order the elements in the diagram. So then Captain America starts in 1940, and we go all the way back to 2020, I believe. As it turned out, the dataset that we had received for the task of visualization was one of those many cases where simply putting the connected data directly on the screen is not the best choice. But now that we have a good understanding of the way that the data is stored in the data source, we can transform the graph and create a different diagram out of it that will be a lot easier to read and includes equivalent information. So what do? Without actually modifying the data in the data source, we use the in-memory presentation of the graph and transform it inside the app to get a diagram that can be understood more easily and is easier to interpret. In this case, we start by tagging each movie node with the universe time it plays in. Then for each of the hero nodes in the data source, we sort all the movies that the respective hero participates in universe time order. And this gives us a list of movies for each character, showing each character's appearance in the universe. And for each 2 movies in those lists, we then create an edge in the diagram. And we tag that edge, give it a label 2. Then the information is replicated and the original hero nodes can be removed from the diagram. And this will result in a graph of movies where the characters actually flow through the graph. And then for this kind of structure, again, the hierarchic layout that we had is a perfect match, highlighting the flow between the various nodes. Looking at the code, the transformation is actually a very simple piece of code. So we iterate over all the hero nodes, and then we query the graph for the outgoing edges at each hero node. And from each edge, we map to the target node of the edge, thus creating a list of all the movies that a hero appears in. We sort each of these lists by the universe time of the movie, and then iterate over the list using the reduce pattern, creating edges between each pairs of edges and tagging them with the original hero node. We also directly add the label to the graph to the edge so that we can see the heroes flowing through the graph. This is what it looks like. Before we set the layout, we get the new structure, but once we run the layout, we get a much different visualization that has a number of benefits. It has far fewer edge crossings, and the number of crossings has been reduced, even though, in fact, when there is a crossing, it even has a meaning and it adds value to the diagram. So when characters move from one franchise or parallel timeline to another, this can now clearly be seen in the diagram. We suddenly see the parallel timelines and the franchises and how they play together. So how streams or groups of characters start and diverge and merge, and when they end, etc. And remember the original visualization that we started from? Try seeing that information in this previous graph. Of course, the duplicated edge labels are still a bit ugly to look at, but we'll tackle that later. As you can see, as a programmer, you have the option to configure the hierarchic layout. In this case, we configured it to work from left to right instead of from top to bottom. And we made sure that the labels, the edge labels, are also integrated in the visualization. For each edge in the visualization, we also told it where exactly to place the label on the edge. In this case, at the center of the edge, and not next to the edge, but directly on top of it. So interestingly, as you may have seen, for this visualization, we did not even have to explicitly provide the layout algorithm with an ordering for the nodes from left to right. The flow of the characters, the edges that we introduced, actually induced a convenient order already. However, we'll just add back a slightly stronger constraint so that visually otherwise unrelated movies from parallel timelines do not appear in the diagram before nodes that play at an earlier point in universe time. As you can see in this example, there's Guardians of the Galaxy from 2014 is on the same vertical axis as Thor from 2018. But adding back that constraint, we get this visualization, and now the movies are sorted in universe time order. We also adjust the size of the nodes to improve the legibility. And last but not least, if we want the user to focus on a single character, we can add more constraints that will actually straighten the path of a character through the diagram. For this, we use the so-called critical edges feature, and we trigger that feature on double click. In the code, you see that registering code for interacting with the diagram is just as straightforward as the automatic layout. So we add a listener for double clicks, and if the user actually clicked on an edge, we call our layout algorithm that aligns the hero that we just clicked on. And the second part of the second code snippet shows how that works. We just the same as before. We're using the additional layout data where we can define priorities of edges. And in this case, we just take all the edges which match the given hero name and give it a weight criticality value of 1, and all others have the value of 0. And with this little piece of code, we get this the movie doesn't play, I'm sorry. We get this visualization where, in this case, Iron Man is neatly aligned at the center of the diagram. The visualization now has become a lot more useful, but visually and from an interactive point of view, it does leave a lot to be desired, of course. So luckily, this is something we can change, and we'll get back to this example later. And we'll now be looking at some of the options that we could use for customizing the visual appearance. With a powerful diagramming software like Y-Files, all kind of data can be displayed right inside the visualization in the diagram. Most of the shelf applications only allow very simple visualizations, but with these solutions, the designer and programmer have full control over every pixel in the visualization. We can show scalar values as text, colors, progress bars, gauges, icons, glyphs, badges. We can add any number of textual information and extra labels and icons. And we can even animate these values. This is very useful, especially, for example, if we can connect to streaming data updates so that the visualization updates live while the user is viewing it. No matter what type and what format the data is in, with flexible and complex data bindings, we can add a lot of information to the visualization, which is great for printouts and screenshots. In this specific example, we're using a third-party data binding engine, specifically Vue.js, but with the open architecture of Y-Files, you can also use other engines like Angular, React, D3.js, or even jQuery or your own templating engine. Most of the shelf applications don't have this ability, and instead you mostly find so-called master detail views, where you get to see all the additional information in a separate properties windows next to the diagram, but they will only ever show the information for the one item that is currently focused or selected. A custom dynamic visualization of the nodes like this neatly solves this problem. On the other hand, in order to not to overload the screen with information, we can even have interactive elements like buttons and lists right in the diagram and use level of detail rendering like this to reduce the visible information once the user zooms out of the diagram. This also improves legibility, of course. Just like for the nodes, we can also change the visualization of edges, labels, ports, and group nodes with the same flexible mechanisms. And of course, we can animate the arrangement process once we apply another automatic layout or when the underlying data changes. Incremental changes, smoothly animated, help the users keep their mental map of the diagram while at the same time highlight the change in the data. But it's not just about rendering the graph elements. Likewise, we can add and change background graphics, render diagrams in isometric views. We can add overlays, maps, imagery, and other utility visualizations in the background or as part of the diagram. And of course, the visualization can react to user gestures with custom highlighting and selection rendering, etc. With layout and rendering covered, this brings us to the third pillar of great diagram visualizations, interacting with the data. Of course, the simple things like reacting to mouse clicks or finger touches, showing custom context menus, searching for elements, etc. are easily possible with customized apps. Basically, any type of action can be triggered through these means. But more than that, if applicable for the use case, diagrams may also be edited interactively with drag and drop, clipboard functionality, undo, redo, and everything. Y-Files supports various input methods like mouse, keyboard, touch, and pen, but you're not limited to actually editing existing data. We can even create our diagrams from scratch. And during this, the application can support the end user with the editing or the creation. For example, by ensuring that a certain schema doesn't get violated, and all modifications are valid according to some business logic. This can be dynamic feedback, which clearly shows that a certain operation led to an invalid state, or we can directly prevent the user from ever reaching that state. And then, of course, for larger diagrams, in order to help with the navigation, we can add additional secondary views. We can add a bird's eye view showing the complete graph and the current viewport. And this is one very common view. Another valuable type of view is dynamic utility views that focus on the current selection or highlight and update dynamically. They can show things like the structural neighborhood in the graph, like child and parent nodes, but they can also show critical paths, for example, for root cause analysis and finding the bottleneck of a network or the shortest path to certain elements of interest. The advantage of these utility views is that they can show a certain aspect of the data and focus on a subset of the elements, showing more details in a small space without destroying the mental map of the user of the complete graph. And of course, we can run some graph analysis algorithms in real time and dynamically in response to user gestures, and then show the results directly in the diagram too. Finally, we can export the results of our analysis and visualization for publication or export to third-party software in case where we cannot or don't want to share our whole app with others. As an application developer, there are virtually no limits regarding the integration of our app with third-party systems. We're not limited to reading data from the typical data sources. We can incorporate and pull data from other live services and automatically update the visualization. But maybe more important, the opposite direction is also possible. Changes to the diagram or interactions with it can kick off all kinds of processes, helping end users with automatic repetitive tasks without ever having to leave their visualizations tool's UI. So now that we've seen what you can do with a sophisticated diagramming framework like Y-Files, let's get back to the Marvel Universe case and see what we made of it. We added an interactive legend that lets us easily switch between highlight and highlight the various heroes, and we aligned the incoming and outgoing edges in the movies and colored them according to the character they represent. We also added character icons to the edges and made sure that the icons are always visible, regardless of the current viewport. And we're using screen time data for line thicknesses of the connections and inside the movie nodes. We added interactive filtering and highlighting options for exploring the graph to let the user focus on a certain subset of the data that they are interested in, so they can see what hero, what movies they should look at, what favorite what their favorite character plays in. And also, of course, we added a background showing the timeline and the dates. You can try the result online at yworks.com/marvel. Be sure to also play with the other demos at yworks.com. And here is the resulting app. As you can see, It's fully interactive. It shows the complete data that we got from the contest, and there's the legend where I can find the elements in the visualization. Clicking on an element focuses that element's path through the movies. Likewise, clicking on a movie can help me show how the characters flow, how the characters flow through the graphics once they play a part of the movie. And all this is interactive with highlights and a dynamic layout. This all runs directly in the browser and can also be run on your smartphone, tablet, and mobile device. Now that's it for my small webinar today. Now I'm happy to hear your questions. I hope you wrote some questions. Let me see. Yeah, there's a few questions. So here's one question. This was all JavaScript. Can I do the same thing on the desktop? Yeah, as I said, Wi-Files is available for basically for all major programming platforms. So we have the web and mobile with JavaScript or TypeScript. And you can also use that to actually create native apps. But also there's Java platform, so you can create Swing and JavaFX or Eclipse RCP applications. And we have the .NET platform covered, so you can create Windows Forms and WPF applications too. So it doesn't have to be JavaScript, but the APIs that we provide for the various platforms is functionally identical. Of course, the syntax is slightly different and the names may be different too, but all the features, all the bells and whistles that we have in the library are available for all platforms as far as there's platform support. So for example, there's no touch support in Swing, but this is because of the platform not supporting that feature. Yeah, next question, is the code available as a demo? Not yet. The code for the simple app that we have will be published soon on our blog. I have that over here. So this is the one that creates the visualization that I've shown in the slides. And as you can see, it's about 200 lines of code with lots and lots of comments. And we'll publish it soon. If you want to, please send an email and we'll get back to you with a link before we publish the blog post. Whether we'll actually publish the full Marvel demo, we need to see, because I think the code still needs some cleanup. And one more question, is it possible to get a recording of this webinar? Yes, there will be a recording. It's probably going to be online, I hope, by tomorrow. There's more questions over here. Finding the right transformation of the data for the visualization can be difficult. Can Yworks help? Yeah, that's true. It might have looked easy in this case, but even this takes some experience. We do offer consulting. However, it's you or our customers who actually have the best understanding of the business domain. So by combining our products with your domain knowledge, you actually create the value. You should really need to carefully find or list the use cases that you have, so that end users can get answers to their questions that they may have quickly. And you need to understand those use cases and the end users. We can then help you with the implementation. There's no generic rule for creating a nice visualization. Is it a pure JavaScript library? Can I embed it in my HTML5 app? Yes, it doesn't actually require an active server component. So it's just JavaScript. It's compatible down to Internet Explorer 9 and but as you've seen in the code, it uses it's also compatible with the modern JavaScript development. So you have things like await and properties and async code and classes and so on. But you, of course, the library itself is directly works even on IE 9, which is the oldest browser that we support. But you need to, at least your own code, you need to babel or transpile it so that the older browsers will be able to read them. But other than that, they only use pure HTML5 technology. The rendering is mostly SVG, but we also support Canvas and WebGL and all at the same time, actually. So it's the library is designed to be embedded into custom HTML5 apps. So there's no framework that we require to be there, but and the library is written to be framework agnostic. But we have samples, for example, that show how to integrate the component into Angular apps or Vue.js or React-based apps or all the toolkits that you know of or may not yet know of. So it's basically what we requires just a diff element and a JavaScript entry point. So I think that's there's one more question. No, I had this one already. I think that's it for this webinar. Thank you for attending, and I hope we'll see you again in one other webinar. Thank you.